Thank you. Thank you. Good morning. So I'm António. This is Mike. We're here today to speak about full stack testing with Om Next and Datomic. And this talk is about how we do testing at Ladder and what processes do we use to make adding features quickly and iterating as a small company. This is not about releasing a new framework. Actually, currently, the implementation that we have is a little bit tied to our internal code base. But we hope to inspire you to at least do some of the things that we do at Ladder. So Mike will start us off giving a little bit of the motivation why we need such a thing, and I'll pick it up eventually and speak about the process.
Cool. So as Antonio mentioned, he and I work at a little company called Ladder. Ladder is rethinking the way that life insurance is sold. Particularly, it's a completely online experience. There's no agents, which is the standard in the industry. The only way to get life insurance is usually through an agent. And we offer instant coverage, which is pretty great because normally a process that's like 8 weeks, we take it down to 8 minutes. So you can get life insurance in the time it takes you to brush your teeth. And as always, we're hiring. But as any Clojure West attendee, we buy into the whole Clojure stack. We run ClojureScript on the client with Om Next as our UI layer. We use Transit to talk to our backend, which runs Clojure and Datomic. So we're end-to-end Clojure. This talk is actually a bit of a riff on a talk that our CTO gave last year at Clojure West, which was full stack testing with Om Next. That one went into detail of how we do what we do with Om Next, and we'll give a bit of an overview here. But the main goal of this talk is to see where we took the framework and what cool things that we did with it. And the answer to that question actually surprised us a little bit. But before we get into the implementation, I wanted to start with a truism. Nobody likes shipping broken code, right? When you ship broken code, it impacts your users, it impacts your company's bottom line, but it mostly impacts engineering, right? Not only do you now have to fix a bug that has made it out into production, you might need to fix any of the data that's now corrupt due to the bug. You have to stay late at the office to do this because this is time sensitive. The entire engineering team is under a lot of stress when this happens. So really what you want is that little red X. For those not familiar with GitHub, that's GitHub's CI marker. So continuous integration, you want some sort of process to prevent you from pushing code that does not work. And the best way we have of doing that is testing, right? But not all tests are created equal, right? Just because you have unit tests doesn't necessarily mean that your application works the way that you expect it to when all the pieces come together, right? Unit tests test things in isolation. But clearly that doesn't always work. So unit tests aren't enough. Going back to the problem that Ladder is solving, Ladder is a little bit different than a lot of the large internet companies like Google or Facebook or Twitter. Those companies, if you ask them, a user to them is worth something between like $5 to $15 a user, right? So when you roll out a canary release and maybe break the experience for 1% of the user base, you're not losing that much money. At the end of the day, it's a loss that you're willing to take. At Ladder, we're selling you life insurance. You might be buying a policy that costs something like $20 to $30 a month, and you're paying us for the next 20 years. So the price that we give to a user is easily in the thousands of dollars. That's not something we want to just throw away. Another corollary to this is something like 90% of our code actually gets run for every single user. A lot of our code deals with going through and getting to the point where we can offer you life insurance, whether you accept it or not. So the code that actually deals with this, giving you a quote, going through the application flow, verifying your identity, generating PDFs, underwriting the user, all that stuff is run for every single user. So we need to have really, really high, really low bug rate for that, because if anything breaks in that flow, the user is stuck. There's nothing else they can do. We have a very linear flow. So the problem that we want to solve is that bugs, for us, actually kill the user experience. So we need tests that can catch those bugs.
In life insurance, we really need to ensure the safety and privacy of our customers. At Ladder, we believe that correctness goes a long way to achieving that. So we need as much coverage as we can get from tests to give us as much confidence as possible that a user's personal and health information is not at stake. And as a company that iterates very quickly, we're always adding new features, and the specification is ever growing. We need our tests to be end-to-end so that the entire stack is exercised. We need them to be decoupled so that when we add a new feature, some tests in the middle of the stack doesn't break or we don't need to fix it. We need them to be lightweight as well, because we're running these tests on every commit, or even before committing, running them on our local machines. And we want them to be easy to write, just because nobody likes writing tests. Let's take an example, a very simplistic flow through our application as an example. Say a user goes to ladderlife.com, clicks the get quote button, fills out their personal information, and sees a quote, which is this one, right? So this is a very simplistic flow, and initially we chose it to model this as just a sequence of function calls returning a resulting state that we can assert on. So right there you see we're calling something called a starting test universe. We call a universe for us is something that has the entire state of our system. So it might have at any point in time the database connection, or email senders, or Kafka workers, all that. We're threading that state through a bunch of calls to opening a new browser tab, loading a route in our application, performing a mutation, a state transition that submits a quote, and asserting something on the resulting state. And this is what we started with, but we quickly found out that it's not really helpful to reuse combinations of these steps. So say we want to take this and get farther away in the application flow. The way that we chose to model this initially didn't allow us to do that, or not easily. So this is also not easy to write. So we want something better. And better in our use case is something that lets us match data at specific points in the app flow with our expectations. And we want to describe the steps that a user takes in our application declaratively as data. Essentially, what we want to do is model the user. So we chose to describe a user action, an action that a user takes on our application simply as a keyword. So load route is a keyword. Open a new browser tab at the root endpoint is a vector of keyword and arguments. A sequence of steps in this model would look like this. We'd open a new browser tab at the root endpoint. We load the route, get quote. What this lets us do then is create a new sequence of steps that reuses the first one that we had to get us further away in the flow to assert new things. So essentially, the new browser call you see there is exactly the same as we had in our previous slide, with the exception that we're now we don't need to create a new test universe. The framework takes care of creating that for us and threading it implicitly through all the steps that we write. Mutate here is a state transition, and this refers specifically to Om Next. So we're going to go through a very quick whirlwind tour of Om Next to help us better understand how this works. So Om Next is basically just a React wrapper written in ClojureScript. But what it provides us additionally, besides being a React wrapper, is something, a component that we call the parser. And you can just think of the parser as a pure function that takes a state and a query. And the query is just a way to express our UI component requirements. So you take that, and the parser takes care of hydrating that query with the component, the data that is our app state, returning the UI data tree that we pass to the React render function. One thing to note about the parser is that it sits at the edge of the system. And so it provides a way for Om Next to do a bunch of optimizations. And also, as Tim Baldridge referred yesterday in his talk, it abstracts asynchrony from the application developer. A query in Om Next can be just a read, which means give me a person's name, or it can be a mutation. And a mutation is just something that changes the state of the system. They're effectively reified state transitions described as data. The parser executes them both on the front end and the back end if they cannot be satisfied locally, and feeds the result of these mutations back to React's render target. So in Om Next, the data tree matches the UI data tree, which means that we can now treat the DOM as a dumb render target and abstract it away entirely in our tests. So the separation between getting and transforming data that is in the parser, sending it to the rendering target, is what enables us to just ignore the render target entirely, and this is where we hook our tests. So we write our Om Next parser in CLJC, and we run our tests in a single JVM process. We mock out HTTP servers and HTTP requests, and at every step of the flow, we execute a mutation against the client-side logic. We send a mock request to the server if need be. We store the data we get back from the server, and we can make assertions on that data at every step in the flow. One thing to note is that this only works if the majority of your logic, or your client-side logic, is in the parser, which happens to be the case in Om Next. It suggests you put all your logic in the parser and treat React or whatever rendering target you're rendering to as just a function from UI data tree to DOM.
Cool. So now that we have this little bit of like a step framework, what do we actually get from it? And the answer actually surprised us a little bit. The first thing that we got is actually the name of this framework, which is teleports. The reason why we call it teleports is because originally when we wrote our tests, we had an idea of just taking our tests and running them in order to move our development server into a particular state. So, for example, if you wanted to fill out the quote form, what you could do is instead of using a test fake universe, you can use your local development server's universe, right? You run the teleport as you normally would. You take the cookies and the client state and send it back to the browser. So, for example, in your local development, what you could do is open the ladder app and click a special key combo that we have for our development, which gives you a list of teleports. And you can run one of them. So the cool thing here is that this teleport that we ran here is actually going through the entire application flow. Now, if you remember correctly, I said it takes us around 8 minutes to get through this flow. If engineers had to wait 8 minutes to get through a flow, and that requires a bunch of typing too, if engineers had to do that, I think they would revolt. This teleport actually takes about 2 to 5 seconds, which is pretty cool. But there's another pretty cool thing about this. So this isn't just a snapshot of what this page would look like. Your local state, both the development server and your client-side state, is completely in sync and genuinely believes that you have a user in this state. So for example, if you were to accept this life insurance offer, you would see what would happen, which would take you to your account page where you have a policy with us, right? This isn't just like a view of what the state would look like. Your local development server is actually in that state. And that's pretty cool. We've used it to both develop UI and test out certain flows that are hard to model otherwise. But once we had this little system of, what if we run a teleport on our local development server, we started thinking that maybe why just limit ourselves to development, right? One thing we could do is instead hit our local HTTP server directly. We were already modeling cookies and headers, so why not just use CLJ HTTP to hit your local server? And we did that, and surprisingly, it worked. It actually surprised us a little bit. But then we said, okay, well, if we can hit our development server, why not hit our staging server? And here we got something pretty interesting. So what we can get from this is load testing. Because we describe our teleports as the steps that users would take when they go through our website, all we have to do to get load testing is pick some of them, annotate them with relative weights of how frequently this particular flow is taken, and all we need to do after that is run them in parallel, hitting a staging server. And we have load testing. That actually is how we do load testing at Ladder. And that's pretty cool because if you've ever worked at a place that did load testing, it's almost a dream to have your integration tests that run for correctness also work as load tests that run to test your server under load. And this framework lets us do that. And that was pretty cool. We call this the remote driver. It's changed the way we do production readiness. It's pretty great. So that's one thing that we get, which is pretty cool. Another one that's pretty easy to see also is once we started doing load testing, which is parallel HTTP requests, parallel teleports, we were thinking maybe we could just run our tests in parallel. Pretty easy, right? Turns out it works. We use Datomic as our database. Datomic has an in-memory implementation, and you can create as many of them as you like. So each one of our tests gets its own database, and it just works. We didn't really have to do much. But there are some caveats, of course. You have to make sure, if you're running tests in parallel, that all state is local to components. We use Stuart Sierra's component library, so things like mock Kafka and fake S3 need to be componentized. We can't use global state. Luckily, the Om Next parser doesn't use global state. It's just a function, so we don't run into any issues there. But consider something like with redefs. With redefs is global state. It's not just binding. So you have to be really careful to not use it because the errors that you get when you mess with global state and parallelism are frightening, to say the least. But assuming you do all that, which it wasn't terribly hard for us, you can just grab all of the teleports PMAP, and you're done, right? All of your tests are running in parallel. So one of the things that we actually did this, and one of the things that we saw pretty early on was that we were doing a ton of duplicate work. And what I mean by duplicate work is the Ladder flow, generally all the possible ways that you can go through an application at Ladder, is pretty limited from a client-side perspective. So a lot of flows would go through the application and then fork depending on what they do next. And this actually ended up taking a lot of time. We were rerunning going through the application 50 to 100 times every time we built all the teleports. And that wasn't great. It started slowing us down, but I'll talk more about that later. But before we get there, an interesting thing that we got from our teleport testing is what we called snapshots. Snapshots are kind of like static views of particular points in our teleport. So what we could do is annotate a particular step in a teleport with a name. So like, for example, one of these teleports has an annotation called decision, which was the page that you saw previously. What that is basically a point where we look at the client-side state and render it. to a React render target, both on the client side and the server side. So CR is client rendered and SR is server rendered. We use Om Next, and Om Next is server-side rendering, which is pretty cool. We just actually just say render the same thing that we do on the client. And what we got from this is actually a little bit surprising. Our designers would use this as the source of truth for figuring out what the different app states look like whenever they need to find out what they look like, right? Instead of going through the flow hundreds of times to figure out what we might do, you can just look here. So in a lot of ways, this actually replaced a lot of usages of dev cards for us. The reason being, dev cards were a little bit hard to maintain for us because they weren't running as tests. In a lot of ways, dev cards would not represent the current state of the world. You know, they would be passing parameters that would be completely out of date for that UI component. So instead, using snapshots, which run as tests, we're sure that there's no way that we can get out of sync. The UI that snapshots render are exactly what users would see. So as I mentioned before, not everything was awesome. Building all this stuff, which is one of the steps in our CI pipeline, started taking a lot of time. We regenerate teleports on every commit, and it was starting to take 8 to 10 minutes when we started looking into it to regenerate all the teleports. Now, 8 to 10 minutes isn't like a terrible amount of time, right? We're not talking days here, but consider that this happens every time you commit. We run tests on every commit, and moreover, we make sure that when you merge into master, you're up to date with master. So not just conflict-free with master, but up to date. So as soon as you have several PRs out there trying to be merged, it takes a long time before you see your commit merged if your tests take more than 10 minutes to run on each one. So this was starting to suck a little bit for engineers, so what do? We're like, well, maybe we can fix this. We know we're repeating a lot of work, right? We're going through the application 50 to 100 times when we can go through it like twice at most. So wouldn't it be nice if you could just kind of like cache it, right? We have this like run step function that runs a step on a universe. Wouldn't it be nice if you could just like put a memoize on it and we're done? That'd be cool, right? Turns out you can't quite do that. One of the things, as António mentioned, that we keep in our universe is the Datomic database. It's an in-memory database, but it's still a database. And turns out you can't really hash a database, especially one that's mutable. We're sort of aware of this. It makes sense. You don't really want to reuse a database between two different teleports that is live for both teleports, right? That would be like doing completely disparate things on the same data, and it would just not work. So what could we do? These are stateful components, so we can't really treat them as values, but there's something in the toolbox for that, right? What if we could clone them? What if we could copy them, right? And we're using steward CR components, so would it be that hard to just make a little protocol that copies stuff? Why not? So we wanted to try it, so let's see how far we got. The first thing that we figured out how to clone was the simple stuff. And I should note that we're only cloning test components here. We haven't actually figured out how to clone a real Kafka instance yet. So the simple stuff, right? We have an email client that's used in tests, which is a mock email client. We don't actually like to send emails from our tests. It just records all the emails that are sent. So in order to clone it, just make sure to copy that atom where it stores all that stuff. Pretty easy, right? Not much there, just make a new atom. One thing I should point out is because of closure structural sharing, a lot of the memory here is actually shared between the two instances of the record, which is pretty convenient when you're running hundreds of teleports in parallel. So we got the very simple records. Next, we realized that our steward CR system map has system maps in it, so it's a little bit nested. So we figure it's probably a good idea to be able to clone system maps. Well, it turns out it's actually pretty easy. If you look at steward CR's component, there's this wonderful function called update system, which actually runs through the system in dependency order, which is exactly what we wanted to just clone it. So this ended up being like 4 lines of code. It's pretty awesome what you can do when the library does everything for you. But as I mentioned, there was one little snag that we were hitting, which was Datomic. What do you do with Datomic? How do you clone Datomic? Turns out, like all good Clojure things, there's a library for that. So there's a library called Datomic by a guy with a very interesting name, Val. But the cool thing about it is it allows you to fork Datomic connections. So what does that do? If you look at Datomic, Datomic's core primitive is the database as a value. So that means that when you have a database instance, it is frozen in time. You cannot mutate it. The only way to mutate a database is via a connection. So if you have a database as a value, that's pretty nice, right? Because you don't have to worry about it changing while you're passing it into different functions. It's all fixed at a point in time. But Datomic actually exports a little known function called the Datomic API with. I think it was mentioned in a talk yesterday. But one thing you can do with is given a database value and a transaction that you want to run on it, it will give you a new database value with the transaction applied, but not to the connection that the database came from. It gives you an as-if view of the world. So you can ask questions like, if I were to run this transaction, what would the database look like? And that's pretty powerful, right? You can use it for a lot of stuff, but in this case, what you can do is fork Datomic connections. All you have to do is, instead of keeping an in-memory Datomic database, you keep a database value in an atom and use with in order to update it, right? That's actually what Datomic does internally. The whole library is like 50 lines of code. And it's pretty awesome that you can just do that, right? We didn't actually do anything here. The Datomic library did everything for us. So, actually, this pretty much is all that we needed to clone. Everything else falls into either being system maps or effectively atoms. So, what can we do? Can we implement Memoize? Yeah, sure. So, I mean, this is actually very close to the actual code we use to implement memoization for our steps. All we need to do is create a key, which is basically where you came from and what you're about to do to the universe. Put it into the cache only once. So make sure you don't overwrite it. Otherwise, you're just doing the same thing multiple times. Clone the system and save the key. Right? This is actually extremely close to what Memoize does internally. And the reality of it is Clojure did all the work for us. So we actually did this. We did implement it. And the pretty cool thing that we saw was at the point where we released this update to the teleport system, our teleports were taking somewhere between 10 to 12 minutes to run at that point because people kept adding stuff. After we pushed this change to just memoize the steps, we weren't even doing anything smart particularly. We just replaced the function call. It started taking about a minute to run all the teleports. So pretty good reduction, I'd say.
But then again, there are still a few caveats with our approach. And in the next part, I'll be going through a little list of what those are and explain how we try and minimize them or even get rid of them entirely. So the first thing to mention is that our end-to-end tests run in a single JVM process. This means that we don't really get to test the code that is going to run on a JS engine, for example, while running our full stack tests. To minimize that use case, we have specific namespaces, for example, namespaces that do number calculations, which have different behaviors according to the engine you're running it into. And so we run these namespace tests both on the JVM and in JavaScript through Phantom, for example. Full stack tests also mean that they're not really integration tests. What this means is that when we're running our full stack tests, we're mocking everything out, such as our email workers, the things that post to our Slack channels. We don't really exercise the code that is running in production. But as Mike mentioned before, we do have the remote driver. So by pointing our full stack tests at our staging environment, we get to exercise that code and see if everything is working correctly. But by having our tests run in a single JVM process, it also means that we do not get to test a bunch of things. For example, we're not really exercising the HTTP parsing server code or the AJAX clients or how clicking buttons in our UI trigger browser events. We think this is actually not the worst problem we have. And to counter this, we actually run the remote driver and Selenium tests on browser stack before merging into master. And we feel like it has caught certain little bugs that wouldn't have been caught otherwise, and we're happy with it. In the future, we're thinking about making our framework a little bit better through, and we have some options for that. The first one is integrating closure spec, for example. As you saw in the previous slides, our teleport steps are just data. And spec knows how to generate data. So if we spec out our teleport steps or we spec out our Om Next mutations, we have the ability to run generative testing on mutations that actually exercise a lot more than just our teleports. We're still trying to find out what the best balance on that is, because it would possibly make running our tests slower, and that's what we've been countering. Ad hoc or incremental teleporting is also something that we're thinking about. And that means, say we have a production bug, and we know what is the exact step that took for the bug to occur. We're thinking that if we can pull out the entire state from production, run that locally, and reproduce the bug locally, that would be incredible to find bugs early and fixing them instantly. Extracting this from our internal code base is also a goal, but you need to be aware that there are certain conditions that our code base has that yours may not have. First thing is we use Om Next, but I suspect you could also implement state transitions in any other framework. The other thing is we're using Datomic, and all the cloning process might be needed to be adapted to your particular use case. There's something else we're considering doing to even make our teleports a little bit faster. So as Mike mentioned, we're not doing any repetitive work anymore. And so we actually took the Loom library and we graphed out the dependency graph of running out our teleport steps. This is the entire view of it. This is the graph 10 times bigger. And then this is it 100 times bigger. So bolded nodes mean steps that are run a lot more than the others. So we're thinking that if we can go through a teleport in dependency order and run all the steps that are common with every other teleport first, we can get those in cache before any other step is run, and possibly take a lot of speed-ups for free just by doing that. There are a few takeaways from this talk. The first thing is, if you've never watched Rich's The Value of Values talk, I highly recommend you do that. As he so well put it, we're actually living in the space age. We can afford to spend memory and storage to run tests, to store things. We actually store our snapshots with every git SHA so that our designer can go back and forth and see if there are any UI regressions. And we can afford to do that, and I think you can too. So if you haven't watched the talk, then again, I highly recommend it. Another thing we found is Datomic is awesome. Where else have you heard anyone speaking about forking entire databases? Describing our steps as data and closure's homoiconicity has also helped us a lot here. This is kind of optional, but the way that we chose to describe our teleport steps as data, convert them into code, and implicitly thread our state through them has helped us immensely in making our tests easy to write. Describing Om Next state transitions as data was also something that was incredibly valuable to us and might even be in the future when we're thinking about generating tests and speccing out all these things. And then again, immutability and the structural sharing that comes with its implementation and closure has also revealed extremely invaluable so that we don't run out of memory on every test run. A fun takeaway from our process is that we can actually now just ditch our IDEs and just commit code from GitHub and be certain that we have coverage for that. I'm half joking, but sometimes we actually do that. Most importantly, we feel like, although our application, we're incredibly proud of it, and we think it is a very cool engineering piece of engineering, we feel like in 2017, everyone can build a web app, and that's not what we're most proud of. We're actually proud that applying this process, having this incredible amount of coverage, is what makes it possible today that we can iterate on our application, add new features, do large refactorings. And this has been so simple and so faster than everywhere else I've seen. Thank you.